A long time before the voyages of Magellan and Columbus, people were traveling over the greatest ocean on our planet. Without compass or chart, Polynesian sailors ranged across the Pacific, guided only by the sun and stars, and most amazingly by the direction of the long ocean waves called swells. Once started, swells travel for great distances in straight lines, creating a navigational grid for those trained to use it. But what causes these great, slow-moving undulations in the ocean's surface? The answer is that somewhere over the horizon, there are strong, steady winds pushing the water into these long waves. The same winds that hundreds of years later allowed European sailors to explore the world. It was around this time that global wind patterns were mapped. Today, atmospheric scientists are studying wind patterns for different reasons, like forecasting the weather or predicting changes in climate. Twice each day, at over 500 stations in the Northern Hemisphere, weather balloons are sent aloft to measure wind speed and direction high in the atmosphere. In recent years, these wind observations and other data have been fed into computers in order to picture global wind patterns. This is a typical January flow pattern over North America. Yellow arrows indicate wind direction. Balloon data shows something else. The winds aloft and winds near the surface often blow in different directions, something you can see by watching clouds. But what causes the atmosphere to behave this way? To find out, atmospheric scientists have used everything from water tanks to weather satellites. The satellites are amazing tools. Each is positioned to complete a revolution every 24 hours, which keeps it directly over one spot on Earth's surface. Pictures, made every 30 minutes, are transmitted to a ground receiver. Sequenced into a time-lapse recording, they give us a revealing view of our atmosphere's behavior. It's clear from these pictures that global circulation falls into patterns. Lying in the planet's equatorial region, there is a region called, since old sailing days, the doldrums. The doldrums are warm and humid, and the winds light and unpredictable. On either side of the doldrums, the trade winds begin. They were responsible for sending out the swells used by the ancient Polynesian navigators. Further toward the poles are calm zones, the horse latitudes, hot and arid with few clouds. Modern voyagers orbiting above the horse latitudes usually get a clear look at the barren land below, for in this zone, in both northern and southern hemispheres, lie the world's great deserts. Next comes the mid-latitudes. Here, the winds blow mostly from west to east. These prevailing westerlies bring a succession of alternating storms and clear weather. These circulation patterns are related to the extreme change in temperature between equator and poles. Simulating these temperatures with a model Earth and a tank of water may give us clues as to how these differences in heating affect circulation patterns. We are using a heat lamp to represent the sun at the equator and injecting a milky fluid into the water to show the circulation. Ice at the sides represents conditions at the poles. Speeding up the action will show any flow patterns that develop. A current of warm water begins rising and moves out toward the poles. Then, as it cools, it sinks, creating a return current. This kind of circulation, put in motion by heat, is called convection. The heat lamp has created two convection cells, one on each side of the equator. But is this a good model of what's actually going on in the atmosphere? The satellite shows that winds do not travel on a north-south line between poles and equator, as would be the case if this were a simple convection cell. Something is deflecting the expected north-south flow. To discover the cause of this deflection, just imagine an Earth-like planet with warm equator and cold poles. If the planet were not spinning, surface air would be expected to move in a straight line from pole to equator. But set the planet rotating, and the same line follows a curved path. This deflection caused by rotation is called the Coriolis effect. So two factors affect the atmosphere's circulation: convection, produced by temperature differences, and Coriolis effect, caused by Earth's rotation. But to what extent does this explain the global circulation patterns we observed earlier? At the equator, warm rising air should produce weak surface winds, and it does, the equatorial doldrums. The warm rising air forms clouds that lose their moisture in daily tropical rainstorms. Air in the descending part of the great equatorial convection cell should therefore be dry, and because the descending air is being compressed by its own weight, it heats up. This heat produces the globe-circling zones of deserts in the Horse latitudes. The return flow along the surface is strong, steady, and deflected by Earth's rotation, forming the trade winds. But not all the air in the convection cell returns to the equator. Part travels poleward and is deflected by the Coriolis effect to join the prevailing westerlies that flow through the mid-latitudes. In the northern hemisphere, continents with their great mountain ranges tend to slow and break up the wind pattern. Below the equator, there is less land to get in the way, so the southern hemisphere westerlies have a chance to build into fierce winds, stirring the ocean into crashing waves. But even faster winds have been found at higher altitudes in both hemispheres. Sometimes you can see evidence of these mysterious winds far above the clouds. Their presence is sometimes indicated by the drift of aircraft vapor trails. Here, a trail is being carried sideways at close to 100 miles per hour. These narrow rivers of fast-moving air are known as jet streams. High-altitude jet streams may have a strong effect on the weather below, and the great rotating storm systems called cyclones characterized by low-pressure centers. Theories that link cyclones with the jet stream are complicated. But what scientists have shown is that the jet stream plays a role in the birth of these huge storm systems. Earth is not alone in having a well-defined global circulation. For example, the cloud bands of Jupiter show remarkably clear atmospheric flow patterns. A feature known for 300 years as the Great Red Spot is a huge swirl of atmospheric gases. In a time-lapse study, we can see the motion of this vast cyclone. Our own global circulation patterns are striking when seen from space. But you can also observe global wind patterns from the surface. Advancing weather fronts and the flow of clouds across the sky are reminders that we live beneath great rivers of moving air.